Okay, so we will now continue our observational overview of active galactic nuclei. And today we are going to talk about the topic of AGN evolution. I'll start with some overall context as usual. And in this course so far, we have spent a lot of time talking about the various physical components that make up an active galactic nucleus. We've talked about the black hole region, we've talked about jets, we've talked about the accretion disk, we've talked about the broadline region, we've talked about outflowing winds and the narrow line region, and we've even extended out to where we've talked quite a bit about the host galaxy. And today we are going to move out to even larger scales in this AGN powers of 10. We have extended things out when we've considered the very large scale jets and lobes out to sort of megaparsec scales. But we are now going to extend out by another several orders of magnitude out to gigaparsec scales. What you're seeing here, just as one example, is the center of the 7 million second Chandra observation of the very well studied Chandra Deep Field South region. Many of the X-ray sources that you're seeing here in this image, which is the deepest X-ray image we've ever made of the distant universe, are active galactic nuclei, and redshifts have been measured, and these AGNs span the range from about 0.1 to 5 or so in redshift, again reaching gigaparsec scale. So we're now considering large numbers of AGNs as samples and trying to understand them in bulk. Another useful diagram for extending out to these sorts of scales is this very nice one. This is the map of the observable universe, derived significantly at least from Sloan Digital Sky Survey data. And these blue points out here are quasars from the Sloan Digital Sky Survey out at redshifts of 1 and 2 and 3 and 4 and so on. And they extend to lower redshifts as well. And you can see we're talking about look-back times now of many billions of years. Here's another nice example for setting this kind of physical scale. This is the logarithmic map of the universe put together by Gott et al. And you can see that the Sloan galaxies are plotted here, and then the Sloan quasars are being plotted out here, and you're talking about distances from Earth of thousands of megaparsecs. So we're out to sort of gigaparsec scales, generally the largest scales over which we study active galactic nuclei in the universe. Okay, so we're going to talk about evolution of AGN, but evolution of what exactly? Well, today we are going to be focusing on the evolution of the number density of AGNs in space measured over cosmic time. So it's kind of like a demographer taking a census of AGN out in the universe. So we're interested in the number density of AGNs of a given type, okay, over cosmic time. That's what our emphasis is on. Thankfully, other aspects of AGN don't seem to evolve that strongly. For example, the basic emission properties of AGNs, for example, their spectral energy distributions or their emission line properties, these seem to evolve rather little, or in some cases not at all, at least measurably, over the vast majority of cosmic time. These types of properties have been measured pretty well now with large samples from the local universe out to redshifts of about 5. The emission properties don't seem to change very much. And this is an enormous simplification, because the fact that these don't seem to be changing very much lets you focus on evolution of the number density of AGNs, for example, without having to worry about trying to unwind additional complications that would arise if the basic emission properties were strongly changing over cosmic time, because you'd have to then work out the changes in emission properties and the changes in the number density simultaneously to be sure you weren't introducing biases into your samples and so on. But thankfully that doesn't seem to be the case, and we can really focus pretty cleanly on the number density of AGNs. Now, another essential sort of point of context is that studies of AGN evolution are driven to a great extent by AGN surveys. These are some slides, just as examples here, from lecture number 2 of this course on, again, AGN surveys. And I would suggest that you first of all go back and, if you haven't seen that lecture, watch that lecture before continuing further on with this lecture, because it really is quite essential, these AGN surveys, for conducting studies of AGN evolution. And in fact, many of the same people that do the heavy-duty AGN surveys work are the same types of people that are doing the AGN evolution studies. These types of scientific analyses often go hand in hand with each other. And indeed, many of the AGN evolution measurements are used to motivate the need for additional AGN surveys. And indeed, our measurements of AGN evolution can only be as good as the underlying AGN surveys that are being used to make the measurements. And today, I am going to focus on AGN surveys that satisfy a number of important properties. I'm going to focus on AGN surveys that find AGNs uniformly. So you have some sky region and you've surveyed it down to some pretty uniform sensitivity, and you can generate uniform samples of AGNs over that sky area. Furthermore, I'm going to focus on AGN surveys that have a well understood selection function. These are surveys whereby you can predict pretty well what types of AGNs you think you should be finding without making a lot of mistakes or mischaracterizations, and what types of AGNs you think you will not be sensitive to finding. That's the selection function. And you need to understand your selection function if you're going to try to make real measurements of what AGN evolution is like out of the distant universe. You also want surveys that have well-measured redshifts for most of the AGNs that are found. That is, of course, essential for identifying where an AGN is out in the universe, and thus what the number density of AGNs at different redshifts are. You need to have well-measured redshifts. These can be spectroscopic redshifts. Sometimes very good photometric redshifts can also be used, but you need well-measured redshifts in one way or another for most of the found AGNs. And then also, I'm going to be focusing on surveys that allow reliable AGN characterization. Things like characterization of the intrinsic luminosity of AGNs. Now, you might be tempted to say, well, isn't that a simple thing? Don't you just measure the flux and then multiply by 4 pi times the luminosity distance squared? Well, it's unfortunately not as simple as that. I will remind you from our lecture again on finding AGNs that AGN appearances can be complex and deceiving. We know that you often have anisotropic obscuration present in AGNs. This is the schematic that we talked about when we discussed the obscuring torus, and that is in quotes because it's no longer strictly just pure torus structure anymore. It's likely a clumpy disk and a clumpy wind. Again, you can learn about that in lectures 7 and lectures 5 of this series. But anisotropic obscuration can strongly affect the appearance of an AGN, and you have to correct for that obscuration before you can measure the intrinsic luminosity of an AGN. In addition to obscuration by an obscuring torus, you can also have obscuration by outflows, which are often present from AGNs. You can have obscuration by the accretion disk itself. You can also have obscuration by material in AGN host galaxies. All of those things need to be taken into account and corrected for before you can measure, for example, the intrinsic luminosity. Another way that characterizing AGNs can be challenging is if you have fundamentally anisotropic emission. For example, we know that blazars, as we talked about when in the lecture where we talked about jets, are cases where a jet is pointed directly along your line of sight, and you can have greatly boosted emission compared to what the true underlying power of the source is. And that can confuse measurements of luminosity, and these types of effects have to be corrected for before you can start reliably measuring AGN evolution for systems like this. There also can, of course, be intrinsic emission anisotropy of the AGN accretion disk. The accretion disk likely has some limb darkening effects. These have to be taken into account if you try to measure intrinsic luminosity. So reliable AGN characterization is a challenging thing. Another example I'll just mention briefly is that in systems, lower luminosity AGN systems, sort of low to moderate luminosity AGNs, are cases where the host galaxy can make a substantial contribution to the total light from the system. And here is a case where you have an AGN that has excellent photometric measurements across many bands, running from the far infrared through to the mid-infrared and near infrared and the optical and the ultraviolet, and then the X-ray. And by fitting models for an AGN spectral energy distribution and the underlying host galaxy spectral energy distribution, you can hopefully unwind the contamination by the host galaxy to get at the true AGN intrinsic power. So that's another way that measurements of intrinsic luminosity can be very challenging. And again, I'm going to be focusing on surveys where that type of very challenging work has been done. So all of these criteria, these 4 that I have listed here with bullet points, these are demanding criteria requiring much effort. But if you can satisfy all these criteria, your survey can be very powerful indeed for studying the evolution of AGNs over cosmic time. Now, I will say that less informative constraints upon AGN evolution can sometimes still be set, even when these criteria are not all satisfied. For example, if you don't have well-measured redshifts for your sources, you can still measure their so-called number count, the number of sources you find as a function of flux. You can model that for various assumptions about AGN evolution and set some constraints, but they're considerably less informative than the AGN surveys I will focus on, where all of these demanding criteria are indeed satisfied. Okay. And thankfully, our multi-wavelength AGN surveys, after a huge amount of work by the whole community, now capture, we believe, the majority of cosmic supermassive black hole growth out to redshifts of 4 to 5 at least. And this, we believe, represents the majority of all the supermassive black hole growth over, all of cosmic time. In other words, we think that the additional black hole growth at redshifts above 4 to 5 is small compared to the black hole growth at lower redshifts of 4 to 5 and below, as I will show in more detail in a little bit. And so we believe that our surveys capture the majority of black hole growth that has ever occurred over the entire history of the universe, which is a major triumph of astrophysics. Indeed, we now believe that our surveys are sufficiently sensitive and sufficiently well developed in terms of gathering all these critical multi-wavelength data, correcting for obscuration, correcting for anisotropic emission, getting the host galaxy light separated out from the AGN light. We think that our surveys are sufficiently well developed in those senses that we now have the necessary tools to settle many of the key questions about AGN evolution over the majority of cosmic time. And that's what we'll talk about today. And indeed, there have been many big successes over the past, say, 2.5 decades coming from these AGN surveys. I've just listed some of them here. I also talked about these briefly in the lecture on AGN surveys. But we now know, and I'll talk about many of these later on, we know the contribution of AGNs to the overall cosmic backgrounds of the universe. We believe we have now revealed most, or at least much, of obscured supermassive black hole growth in the universe. Our understanding of AGN evolution has totally changed on account of the improved surveys over the past 2.5 decades. And furthermore, this has led to an improved understanding of the cosmic balance of power. That is, how much power has been generated since the formation of galaxies by stars versus growing supermassive black holes. Again, I'll talk about that later on. And we also have much better understanding of high redshift AGNs and their contribution to the reionization of hydrogen in the early universe. And we are moreover making strong progress on AGN galaxy and AGN large-scale structure connections. So those are some pretty good successes coming from AGN surveys over the past 2.5 decades. Now, the final sort of point of context I will make is that, as usual, the study of AGN evolution is an enormous field, and I am only going to be able to show some selected highlights from a vast body of exciting, high-quality, ongoing work. There's entire conferences that have significant components entirely focused on AGN evolution. Here are a few examples here, and I refer you to the slides or the proceedings from some of these conferences, for more coverage of this important topic. Okay, so I will start our detailed discussion of AGN evolution by talking about the evolution of luminous quasars. So these are the most luminous AGNs in the universe, ones that are so luminous that you can see them without enormous trouble, at least with modern technology, out to very high redshifts. So I'll just start with a brief history on luminous quasar evolution. Quasars, of course, were first discovered in 1963. And remarkably, and the quasars that were found in 1963, these were at redshifts of like 0.1, 0.2. And remarkably, by just 2 years later, by 1965, the quasar redshift frontier had reached redshift of 2. So that was an enormous expansion of our ability to probe the universe in just 2 years, going from redshifts 0.1 to 0.2 out to redshifts of 2. And by 1967 to 1968, it was clear that the quasar population was evolving strongly. The evolution was not subtle, as we will see, and by any means. And you could see that the quasar population was strongly evolving, even with the very early data that were available. And then, motivated by these very important early results, during the sort of 1960s to the 1990s, AGN evolution studies were dominated by wide field optical surveys of rare luminous quasars. And I'll just show some plots of the types of relevant surveys. These are modern versions of these modern version diagrams showing the sort of sensitivity versus area of sort of modern optical imaging surveys in this slide, and then optical spectroscopic surveys here. And you can see that we have a wide range of surveys running from narrow field, extremely sensitive surveys over here, over to, very wide area, almost all sky surveys over here. And, you can see that the surveys shown here are color-coded, either having been completed in black, ongoing sort of in purple, and then future in blue. And generally, of course, our advancement in optical imaging surveys progresses in this sort of a direction toward the upper right, as better and better technology allows better surveys over larger areas. That's always the direction we're aiming to push to explore the universe better. Of course, going hand in hand with these are the extremely important optical spectroscopic surveys. Here is another similar plot, limiting magnitude versus area, and again with the different surveys color coded. And there are many extremely powerful spectroscopic surveys now, spanning a wide range of solid angle, a wide range of depth, pushing always again toward the upper right, getting larger samples to greater sensitivity over larger areas of sky. Okay. Anyway, so these types of surveys, optical imaging surveys, optical spectroscopic surveys, were the driving force, I would say, in AGN evolution studies during the 1960s to 1990s. Of course, they weren't the only game in town. Very valuable radio surveys of AGN evolution and X-ray surveys of AGN evolution were also ongoing. And these, among other things, helped assess extinction effects. When you look at these optical surveys, of course, you have to be very worried, especially when you go to high redshifts where you're sampling the rest frame ultraviolet, that extinction, even mild extinction, may significantly be affecting your results. And so having radio observations and X-ray observations that are much less susceptible to these extinction effects were very valuable for keeping the optical surveys on track and giving us confidence that we weren't being tricked by extinction effects. Okay, now the first thing you can do, as I kind of mentioned already, when you conduct one of these surveys, even before you have redshifts, is you can just plot the number counts. This is the number of sources you find, typically shown per square degree, as you go down in flux. In this case, this is B-band magnitude, running from 16th magnitude over here down to somewhat fainter than 24th magnitude over here. Obviously, you should go to fainter flux limits. You get larger numbers of quasars being measured. And, to give you some context, the current sort of luminous optical quasar samples generally have sky densities between about 10 and 200 per square degree. So you're sort of probing this range over here, sort of running from, of order 20th magnitude, maybe down to 22nd magnitude, maybe a little bit fainter. That's where a lot of the modern optical quasar surveys are being conducted. And it's worth also noting that the deepest optical quasar samples, down at a little fainter than 24th magnitude, reach about 600 sources per square degree. And it's worth remembering that number for comparison with some measurements I'll show you from other wavelengths later on. Another notable point is that you can see there is a break in the optical quasar number counts. The slope here is steeper than the slope over here at the faint end. And of course, that has implications for AGN evolution. So again, as I mentioned, a survey where all you can do is measure number counts, has value, but it's not nearly as powerful as surveys where you have, again, measurements of redshifts for all the sources, reliable measurements of luminosities for all the sources. So I will focus on those types of surveys, but these number counts are worth always keeping in mind. They're another very valuable tool in this whole surveys endeavor. Okay, so now I will just show you some results from surveys where you do have all the redshifts and so on. And here is one of the most important results that emerges from studies of the evolution of luminous quasars. I'm just showing one example here from Richards et al., and there are many, many other extremely high-quality studies showing similar results. But one of the main results that emerges when you investigate the evolution of luminous quasars is that they strongly evolve over cosmic time. And again, this was known since the late 1960s. And what we know now is that luminous quasars strongly peak at redshifts of sort of 2 to 3, as you can see here. And in this range, they are much more common, like a factor of 1,000 times more common than they are, in the local universe over here at redshift 0. And these plots, this plot shown here, and these types of plots in general, already take out the effect of cosmic expansion. It's not somehow just that the quasars were, more densely packed here because the universe was smaller. That's not the effect that's going on. There was true underlying evolution of the quasar population. Now, in this case, very luminous quasars are being studied. The specific limit here is that you're looking at quasars with I-band absolute magnitudes brighter than minus 27.6. These are very powerful quasars indeed. Now, another sort of way to appreciate this plot, I find, it's probably even more useful than this one. This is the way you typically see it plotted in scientific papers. An even more useful way to plot this is just to plot it in a sort of typical, common sense, Astro 1 textbook way. And here is that version of the same plot. This shows the density of quasars versus cosmic time. Again, taking out the effect of the expansion of the universe when making the plot. Cosmic time in billions of years. And of course, today, we are over here at sort of 13.7 or 13.8 billion years in cosmic time. And you can see that quasars were vastly more common between about 2 and 5 billion years after the start of the universe than they are today. Today, by all measure, compared to how common they once were, they're almost gone. There are a few quasars around us today, but they are very rare indeed compared to how common they were back here. In fact, back here, quasars were so common in the universe that if we were living back here, probably be a very dangerous time in the history of the universe to be living because all these quasars would be going. But if you live back there, you could walk out in your backyard and look up in the sky on a dark night, or maybe with the use of moderate power binoculars, and see quasars. That's how common quasars were back then. They were vastly more common than they are today. Okay, so what causes this remarkable evolution? Well, you can probably sort of reason it out and guess pretty well what causes it. And, common sense expectations turn out to be, as best we understand, about correct. At very early times back here, or going to this plot over here, quasars were not very common because galaxies had not yet really come together and organized themselves well enough that you could feed supermassive black holes very well. So at very early times, quasars were not very common because, again, you had to wait for galaxies to form and get themselves organized so they could feed the supermassive black holes that make the quasars go. That's the basic factor that drives this rarity at very early times, and then the strong rise here is, we believe, indicating galaxies getting themselves pulled together and being able to feed the black holes. I'll say more in more detail about what we know about this early time later on, but that's the idea. And then at late times over here, well, you might expect, well, there's some sort of a problem with further feeding the black holes that have been manufactured. That is, by this point, you've manufactured supermassive black holes via the black hole growth that is represented by all this quasar activity. So there are massive black holes that have now been formed. They're there, but there becomes trouble feeding them. Much of the gas that we believe, the cold gas that we believe was responsible for feeding quasars, as we talked about in the previous lecture on feeding the monster, is now mostly tied up in stars, or it's already been eaten by the black hole, or via some effect it has been removed from the vicinity of the supermassive black hole. That's what drives the late time decline of the quasars here and in this plot shown over here, okay? Basically, the quasars are starved for one reason or another. Again, the gas gets locked up in the stars, so it's not easily accessible to feed the quasars. It's already eaten, or it's removed from the vicinity of the supermassive black hole. And that's what drives the decline over here. That's the basic idea of what we think drives this overall behavior. Now, there's many other important things to say about this plot, and we'll say them soon enough, but I just want to focus on a couple of other things. This plot, if you look at it, is a little bit depressing, because, again, we're over here at 13.7, 13.8 billion years, and this plot is essentially saying the universe had an enormous party back here between about 2 and 5 billion years after the Big Bang, and we missed it over here. And, well, I happen to work at Penn State University, and at Penn State University, telling students that they've missed a party is not a very good thing to say, and so the fact that we missed the party is very disappointing to the Penn State students. Today, in the local universe, it's like we've walked into a room and we find the remnants of a party that once happened. There are balloons on the floor and spilled confetti and spilled streamers and an old pizza box sitting on the floor. But it's pretty clear we've missed the party, which is disappointing. And indeed, here is a newspaper article from the Centre Daily Times, which is our local newspaper, which shows how the Penn State students like their parties, where in this case we were ranked number 1 among the top 10 party schools, as you can see here. So in any case, saying that you missed the party is not a very popular thing to say around here at Penn State. And indeed, I will talk later on about how the situation is perhaps not quite as grim as you would expect just from this plot. But I have to say a few more things about AGN evolution, and we will return to this issue of having missed the party a little bit more later on. And we will see things are not as bad as it appears. Okay, so another point which you want to then understand is, well, is this overall curve of the evolution of the quasar population, is this indicative of the evolution pattern of a typical quasar, or is something more complicated going on? And the answer is that we do not think that this overall evolution curve is indicative of the behavior of a typical quasar. That is, we don't think a typical quasar lives as a powerful quasar for a period of 2 or 3 or 4 billion years, corresponding to this span of time, and grows and grows and grows over that entire span of time until it shuts off. We don't think that quasars last that long. So we believe that this pattern is indicative of the overall population of quasars, but is not indicative of the evolution of a typical individual quasar. That's the distinction I'm trying to make. There's a number of ways to reason out that that can't be what's going on. I'll present one of the most direct arguments that this is not the evolution of a typical individual quasar. And this comes from consideration of supermassive black hole masses. We have now succeeded, as I talked about in the lecture on the broadline region, for example, in measuring the masses of many supermassive black holes out in the distant universe at redshifts of 1, 1.5, 2, 2.5, even reaching up to redshifts of 3. And we find that the typical black hole masses have between about 10 to the 8 and 10 to the 9, and perhaps up to a few 10 to the 9 solar masses, up to a few billion solar masses. That's the range of typical supermassive black hole masses in the universe. This is also found in the local universe. This plot here, which I believe I showed in the previous lecture as well, shows the overall distribution of black hole mass, and this plot is normalized in a way that it shows where all the black hole mass is. And most of the black hole mass is between of order 10 to the 8 and a couple times 10 to the 9 solar masses. That's where the majority of the black hole mass lives. Okay, so then how does that fit together with this evolution? Well, that's what I have written down here. You will remember from our previous lecture on feeding the monster that to power one of these very luminous quasars over here, you have to feed it, roughly 10 solar masses per year of mass. You have to supply that kind of mass to the supermassive black hole's event horizon to keep a luminous quasar powered. And, well, if that sort of mass supply, that sort of accretion rate were provided for 2 to 3 billion years, corresponding to this span of time here, well, you would produce black holes that have 20 billion, 30 billion times the mass of the sun. And that is considerably more massive than what we observe. Okay, that would be up here where my arrow is pointing here, up above 10 to the 10. We don't find lots and lots of supermassive black holes with such enormous masses. We do know of a couple, but they're quite rare. Most of the mass is at lower masses, and that's true in the distant universe from our direct reverberation mapping measurements, and that is also true based upon, again, these measurements of local supermassive black hole masses. So the point is that if indeed this curve represented the evolution of a typical quasar, the masses would come out to be considerably more massive than what we observe them to be. And so that kind of a consideration has led people to believe that the typical quasar lifetimes are likely considerably shorter, are only like 0.1 to 0.3 gigayears instead of like 2 to 3 gigayears. Okay, and that with evolution, with accretion at this rate for that span of time, then you would produce black hole masses much more consistent with what is observed. Now, of course, if that's true, if quasar lifetimes are indeed that short, that implies that there are many generations of quasars, each generation of which might last for 0.1 to 0.3 gigayears or so, that makes up this overall curve. So in other words, there are many generations of quasars coming and going and coming and going and coming and going that makes this overall curve. And indeed, that is what's shown in this nice plot shown here. This is the same plot that I've just been showing you, and this plot over here shows the idea of populations of quasars coming and going, coming and going, coming and going. Each one of these yellow curves would represent, a quasar coming and going, coming and going. And you add up all of these quasars coming and going and coming to go, and they produce the overall pattern that is observed here. That's what we think is going on in a nutshell. So in other words, the rise and fall of the whole quasar population does not indicate the lifetime of an individual quasar, which is much shorter, but instead there were many generations of quasars. Now, if you take that basic reasoning and work it out quantitatively, this also implies that a large fraction of present-day massive galaxies were in fact quasars in the past. Each one of these quasars coming and going represents the generation of a supermassive black hole in the core of a galaxy. And if you do the sums carefully, in fact, you find that the predicted space density of supermassive black holes is quite comparable to the space density of present-day massive galaxies. So in other words, you expect that typical massive galaxies in the universe today should contain remnant supermassive black holes. And that is indeed exactly what is observed. Okay, so that's what we think is going on to produce this overall evolution pattern. Many quasars coming and going produce an overall pattern like this. This is not indicating the behavior of a typical individual quasar. Okay, and in fact, this idea of many generations of quasars coming and going has been around for a long time. In fact, here is a very important paper by Donald Lyndon Bell from 1969 titled Galactic Nuclei as Collapsed Old Quasars, that essentially lays out the idea that I've been talking about here. Some of the details weren't exactly right. This was 1969. This was very early days. In fact, back then, the term black hole was just coming into wide use, and you can see here in this paper, Lyndon Bell refers to these systems as Schwarzschild throats. That word is the word that we now refer to as a black hole. So, but even though these were very early days back in 1969, the basic idea that there might be lots of old quasar remnants hanging around, was well appreciated back in 1969. You can see here, even the little subtitle says, "Powerful emissions from the centers of nearby galaxies, may represent dead quasars." And the paper goes into many details about that. But, these ideas have been with us for a long time. So this is a very important insight, from quasar evolution, that there's been many generations of quasars coming and going, and that so many supermassive black holes should have been generated that your typical massive galaxy, you have every reason to expect there should be a supermassive black hole in there, as was found later on. These predictions were made well before we knew that was the case. Okay, now I have to say a few more words about how we quantify the evolution of luminous quasars. I mean, making plots like this is all fine and good. Plots like this one, this is all fine and good. This is a very useful plot for showing the overall evolution of the population. But you can get better insight by measuring something known as the quasar luminosity function, as shown in this plot. So the quasar luminosity function is practically a measurement of the space density of quasars per co-moving megaparsec per unit magnitude versus, in this case, magnitude or luminosity, okay? Ranging from low power quasars up to very powerful quasars. And you can see in this plot, which is broken down, each of these panels represents a redshift range. There is a measurement of the luminosity distribution of quasars in that redshift range. And you can see all that information is shown in all of these many different panels, and it shows how common quasars of a given luminosity were at a given era of cosmic history. Okay, now the way this luminosity function is written down quantitatively is with the symbol phi here, and this is phi as a function of luminosity and redshift. And the luminosity function is set up so that basically if you integrate over a range of luminosity and over a range of redshift, this luminosity function, and include the cosmic volume in it, well, you perform that integral and you get out the number density of quasars at that luminosity, at that redshift. That's the idea of this quasar luminosity function. It encodes a tremendous amount of information about how supermassive black holes are growing over cosmic time. Now, there's been much work that has gone into trying to model this quasar luminosity function. It is often modeled with a so-called double power law model, although other models are often used as well. But this is a commonly used model where this phi as a function of luminosity at a given redshift is such that it's some constant divided by luminosity divided by a characteristic luminosity, L star, to some power gamma 1 plus another power law with a slope of gamma 2. And that you can see that corresponds to this steep behavior at high luminosities and then the flatter behavior at lower luminosities. The fact that there's a bend or a break in this power law function. This sort of a model does a pretty good job capturing that once you go and fit for the quantities of A and gamma 1 and gamma 2 and so on. And of course, I will mention that galaxies are similarly studied in this same basic luminosity function framework, with some technical differences. But this is a common way that you characterize the evolution of a population of objects, galaxies or quasars, over cosmic time. Now then, there's a number of terms that are used when one tries to describe the type of evolution that is going on. And this is a useful plot from Netzer's book that kind of lays out the types of evolution of the luminosity function that people speak of. So this basically shows the space density versus the luminosity. Here is your characteristic curve at a redshift of 0. That's the luminosity function for quasars, say, at a redshift of 0. It's just a schematic. The axes aren't even labeled, but you see the basic idea. Well, one possible way the population could be evolving is so-called luminosity evolution. Under this type of evolution, well, the basic shape of the luminosity function at a redshift of 0 is retained, but it shifts upward over cosmic time. It shifts upward in luminosity, okay? Excuse me, I misspoke. It shifts rightward in luminosity, okay, over cosmic time as the redshift increases. So luminosity function is shifting rightward here. So that this same basic curve shape would be preserved, but here it is shifted rightward at a redshift of 1. Here it is shifted rightward further at a redshift of 2, and so on. That type of evolution is referred to as luminosity evolution. Similarly, there is another type of evolution known as density evolution. In this case, the luminosity shape at a redshift of 0 is again retained, but now the population just shifts upward, okay, in number density as the redshift rises. Okay, that's another possible type of evolution. And then finally, well, you can have more complex types of evolution where both luminosity and number density change as the redshift rises. And then you get a more complex form of evolution where things don't shift so easily, but there is a broad shifting kind of in this direction in, again, the luminosity space density plane. Okay, now different samples of quasars have been used to model this luminosity function. For luminous quasars, you find that in fact pure luminosity evolution actually seems to work pretty well, often out to redshifts of about 2, where again you just shift rightward here in luminosity, keeping the same luminosity function shape. That seems to work pretty well out to redshifts of about 2, but if you consider broader ranges of redshift, broader ranges of luminosity, generally more complex evolution models are required. Some type of luminosity-dependent density evolution or similar is required to explain the evolution of the luminosity function. And there are various parameterizations of how the evolution works, but generally more complex forms of evolution are required to explain the data. And I'll say more about that once I've talked about AGN surveys at other wavelengths a little bit further. But in any case, this sort of evolution is what is studied using these luminosity functions. And many papers have been written trying to say, well, is it luminosity evolution or density evolution or something more complicated? And the end story, when you consider large ranges of luminosity, large ranges of redshift, is something more complicated is generally found to be going on. Okay, now I'm going to move on and talk about the evolution of typical AGNs, not just luminous quasars, which are the ones that are best studied from the very wide field quasar survey. But now we're going to push to lower luminosities, study the much more common lower luminosity typical AGNs, and I'm going to focus on typical AGNs selected in X-ray surveys. I'm a big fan of these X-ray surveys. I think they have a number of important advantages. One of them, as I've alluded to a few times previously in the course, is that, well, X-ray emission is penetrating and has reduced bias due to absorption. We know that AGN light is usually substantially obscured by both nuclear material, the torus, outflowing winds, and so on, as well as galaxy-scale material. This active galactic nucleus lives down in the core of a galaxy. There is much prospects for obscuration in these systems. Thankfully, X-ray emission is a very penetrating form of radiation, that can penetrate through, and not only penetrate through, but also allow measurement of the amount of absorption that is there, the column densities that are present. That's shown in this little movie here, where here I show a typical AGN spectral energy distribution with no absorption, labeled as 0, and then I add varying amounts of absorption, 10 to the 20, 10 to the 21, 22, 23, 24. And this is the general absorption effect. The low energy X-rays are heavily absorbed. The high energy X-rays are not so absorbed. And again, for context, the column density through your hand is of order 10 to the 23. The column density through your chest is of order 10 to the 24. And you can see that high energy X-rays can penetrate through very large column densities, comparable to those through your body, which of course is why the doctor uses X-rays to take pictures of your bones. Now, this absorption bias with the X-ray approach has another important advantage, and that is it drops as you go toward high redshift. As you go toward high redshift, the high energy X-rays are cosmologically redshifted downward in energy. So in a fixed observed frame band, you gain access to increasingly penetrating rest frame X-rays. And so as you go to high redshift, the absorption effects actually become less and less as you go to high redshift, which is a very important advantage of the X-ray approach. That's very different than what happens in the optical and ultraviolet. As you go to high redshifts, in the optical ultraviolet surveys, you progress further and further out into the ultraviolet, becoming more and more susceptible to dust effects. So the dust extinction works against you as you go to high redshift in the optical and ultraviolet, but it actually helps you in the X-rays, which is a big advantage of the X-ray surveys. And this obscuration and being able to, again, penetrate through and measure the obscuration is very important, because we now know from well-studied surveys that most AGNs in the universe are obscured. Here are just a couple of examples of this. This is a absorption column density distribution here of the so-called CFA Seyfert galaxies. This is a sample of nearby Seyfert galaxies selected based upon optical spectroscopy, and you can see many of these systems have large obscuration levels, column densities of 10 to the 22, 10 to the 23, 10 to the 24, pushing up to even 10 to the 25. Very large absorption levels. Similarly, if you go out to the distant universe, this is the intrinsic column density distribution inferred for the Chandra Deep Field South survey that I showed earlier on in this lecture. And you can see many of the AGNs, most of them are obscured by substantial column densities out of the distant universe. So we believe that most AGNs in the universe are obscured. And so having a method of finding them that deals with this obscuration is extremely important. Furthermore, I will mention that we've in fact studied how this X-ray absorption depends upon redshift, and we find that X-ray absorption levels generally rise with redshift. That makes sense. At earlier times, galaxies were more rich with cold gas, so you might expect X-ray absorption levels would be higher toward high redshift, and that is indeed generally observed. And furthermore, at a fixed redshift, X-ray absorption levels generally decline with luminosity. So at a fixed redshift, as you raise the luminosity, the system clears itself out of absorbing material. Sometimes this is referred to as a receding torus scenario. And so the point here is there are interesting connections with redshift and luminosity that have been extensively studied. But the overall point is that absorption is very important among AGNs. This is direct observational evidence for that, and thus X-rays are a very good way of dealing with that obscuration effect. Furthermore, as I've talked about previously as well, X-rays have low dilution by host galaxy starlight. This is an optical image of a nearby active galaxy. This one, this is the corresponding 2 to 10 keV X-ray image. And in the X-ray band, all of the starlight drops out, and you just see the light associated with the accreting supermassive black hole. This very large contrast between black hole related light and starlight in the X-ray band is extremely important, because when you conduct surveys out at high redshift, this is a local AGN, this is very well spatially resolved, but at high redshifts you don't have the luxury of being able to spatially resolve the AGN light from the host galaxy light, and so you need a form of finding AGNs in the distant universe that maximizes contrast between black hole light and starlight. X-rays give you that, and thus they give you the cleanest AGN samples. And owing to these two basic effects, the penetrating nature of X-rays as well as the low dilution effect, as well as the fact that X-rays appear to be almost universal from luminous AGNs, many X-ray surveys have been conducted. This is another one of these plots of sensitivity versus solid angle, kind of like the ones that I showed you for optical surveys. And many X-ray surveys have now been conducted by a variety of missions, ranging from, again, narrow field, ultra deep pencil beam surveys to wide field all sky surveys over here. And these have all been used to investigate AGN evolution in the X-ray band. Now, the first thing that you show from these surveys, as we did for the optical, are the number counts. These are the X-ray number counts for AGNs. And as you would expect, as you go down to fainter and fainter sensitivity levels, you get higher and higher sky densities per square degree of AGNs. And in fact, the AGN number counts in the faintest X-ray surveys that we've conducted, these are from the 7 million second observation of the Chandra Deep Field South, reach about 23,900 per square degree. Remember, the corresponding number from the deepest optical surveys was about 600 per square degree. Somewhat more, maybe 1,000 per square degree, around there. And so the X-ray method finds considerably more AGNs on the sky per square degree than, for example, the deepest optical surveys. The reason why that's possible is, again, because you find the obscured systems, you don't have this dilution by starlight effect, and that lets you home in on the AGNs very effectively indeed. And we, in fact, have found about if you take this number and scale it up over the entire sky, we expect there to be about 1 billion X-ray AGNs at this very faint flux level over the entire sky. And as I've said, this is about a factor of 20 times higher than the deepest optical AGN surveys. And when we sort of torture test the X-ray AGN selection method versus other methods, versus selection at other wavelengths, the X-rays method does very well, considering its completeness and particularly considering its purity. That is, when we claim an X-ray source as an AGN, we say that with very high confidence, whereas, for example, in the infrared band, where you're studying waste heat, sometimes there can be confusion between starlight heating dust or an AGN heating dust. I'll say more about that a little bit later on. And on account of this, what you can see here in this plot shows the largest AGN surface density versus frequency. And in the radio band, you can get up a little more than 1,000 per square degree. Here is the near infrared and the optical. Again, getting of order 1,000 per square degree, something like that. And here in the X-rays, we're up at 23,000 per square degree. And then it drops off in the gamma ray up here toward high energies. Again, very high energies, like gamma ray energies. So X-rays turn out to be a very powerful way of generating large numbers of AGNs on the sky for the reasons I've described. And all of these surveys that we've conducted have indeed done a great job of sampling a wide part of the luminosity versus redshift space that AGNs occupy. Here are AGNs found in a variety of different surveys, X-ray surveys, and you can see at a given redshift, you span 1, 2, 3, 4 sometimes orders of magnitude in luminosity, giving you a good ability to measure the luminosity function of AGNs at a given redshift. And these histograms show the numbers of AGNs, and you can see we have large numbers of AGNs in these sky surveys, especially when you add all of them together. We have thousands of AGNs per redshift bin or per luminosity bin for studying AGN evolution. So these surveys have turned out to be very powerful indeed. And you find remarkable things when you investigate AGN evolution in the X-ray band, where you can push down, again, to much lower luminosities than you can do with the optical quasar surveys. Here is one of the important things that is found. You find that the evolution of active galaxies appears to be a luminosity-dependent phenomenon. So this plot here shows the evolution of AGNs of different luminosity classes, labeled with colors following this scheme written here. The most powerful AGNs, shown down here, selected with the X-ray method, evolve as the luminous quasars do, as you would expect. They were very common out at the high redshifts of 2 to 3, but then they decline strongly by orders of magnitude and are very rare in the local universe. If you go then to an order of magnitude lower luminosity, this green curve, well, you can see the green curve peaks a little bit later in cosmic time than does the blue curve. But even at this lower luminosity, the AGNs have declined quite strongly by redshift 0. You go to lower luminosity still, however, this yellow curve, well, there you can see the AGNs peak at still later cosmic times, still lower redshifts, and they still have declined, but much less of a fractional decline than happened for the very luminous systems. And then here for the lowest luminosity AGNs that we study with the X-ray method, well, they decline also a little bit, but it's only a factor of several since their peak. So these AGNs are still going strong, at late cosmic times. This overall behavior of luminosity-dependent evolution of active galaxies is referred to as downsizing or cosmic downsizing of the AGN population. This overall downsizing behavior is also known, for example, for star formation in galaxies. Star formation in galaxies also downsizes in a similar way, whereby the more massive systems terminate their star formation earlier in cosmic history than the lower mass systems do. So there's a broadly similar connection between galaxy star formation and black hole growth in galaxies. Even more broadly, in fact, very broadly indeed, this is perhaps only a useful mnemonic for remembering things. The AGNs and the galaxies evolve kind of very broadly in a way, the same kind of way that the stars evolve. You will remember that massive stars do everything faster compared to low mass stars. This plot here shows the evolutionary tracks for contracting protostars, and massive stars contract down to the main sequence on timescales of just tens of thousands or hundreds of thousands of years, whereas the low mass stars can take millions of years, tens of millions of years, even more than 100 million years to reach the main sequence. And then, of course, the massive stars also live their short lives and blow themselves up in short order. And some of these massive stars have lived their lives and are blowing themselves up before the very low mass stars have even made it down to the main sequence. And so massive stars do everything faster. And as for the stars, also appears to obtain for the galaxies and for the black holes. They do everything faster. They come in faster and they go away faster. Okay. So that's a very broad connection, but it's a useful way to sort of remember these things because everyone knows stellar evolution very well. And this behavior is, somewhat surprising. It's kind of anti-hierarchical in nature. You normally think of the universe developing where you form little things, the little things merge together to make somewhat bigger things, and then the somewhat bigger things merge together to make bigger things still, and so on. But this is actually the opposite of that. The really big, powerful black holes came first, and then the lower and lower luminosity, presumably lower mass black holes came later and later. Now, why is this happening? Well, we think this is likely driven by the behavior of cold gas in galaxies of different masses. We think quite likely that the cold gas in very massive galaxies is more flagrantly utilized, exhausted, turned into stars, accreted by black holes in short order, whereas that process takes a longer time in the lower mass galaxies. See Lecture 9 on Feeding the Monster for more discussion of that. And another point is once you weight in all of these lower luminosity AGNs and combine them with the quasars, well, the overall peak of supermassive black hole power production in the universe shifts down to redshifts of about 1.5 to 2 once you add together all of these things. These systems are much less luminous than these, but there's many, many more of them, as you can see from the space density plot. These are much more common. And so once you weight everything up, the peak of power production from supermassive black holes is not at redshifts of 2 to 3, as you would expect from the powerful quasars, but is actually shifted down to more like 1.5 to 2, down around there, which is quite interesting. Okay, so that's a luminosity-dependent evolution of AGNs, which is a very important result that emerged from, again, X-ray surveys and our ability to probe AGNs down to lower luminosities. Okay, I will also mention that you can now see this luminosity-dependent evolution of AGNs from optical quasar surveys as well. Once the X-ray results were out, people at other wavelengths started looking to see if they could see this downsizing behavior in their data sets as well. And if you push the optical surveys quite hard, breaking them up into luminosity classes as best you can, well, you do see evidence for that overall broad downsizing behavior among optical quasar surveys as well. This behavior of downsizing has also been seen in radio AGN surveys and so on. So this downsizing behavior now seems to be a general fact of the AGN population, whether it's selected optically, X-rays, radio, and so on. Okay, so now we can return to this very important question for the Penn State students of whether we've missed the party. And again, this plot kind of tells the story. The really big parties here at Penn State, we sometimes have so-called tailgating parties before the football games where tens of thousands of people gather and party outside the football stadium. And that might correspond to these very luminous systems here. Well, the tailgating parties, well, they're over by redshift 0. We missed the tailgating for sure. Okay. And then we have other parties at Penn State that aren't quite as big. We have a party called State Patty's Day, suitably in green, that is smaller than the tailgating parties, but though that type of a party is also over by redshift 0. The decline has been very strong. But if you move down to smaller scales, like parties that people have at frat houses or the parties that people have in dorm rooms, well, those are still going pretty strong, especially the smaller scale dorm room parties, even at redshift 0. So as I tell the Penn State undergraduates, they don't have to worry so much. We didn't, in fact, miss the party so badly. We missed the really big scale parties, but there's lots of small ones still going. And you can still get in on some of the party action. We haven't missed that. We didn't miss the entire cosmic party when all of the massive black holes formed. Okay, so in any case, that's that important matter. And then I will also just mention a couple of other points. Here is a good quality measurement of the AGN X-ray luminosity function, similarly to what I showed for the optical luminosity function for quasars. So you can see here, again, over a wide range of redshifts, each one of these panels shows a redshift range. You have good measurements over a wide range of luminosity of the luminosity distribution of AGNs. And you can see, and the redshift 0 luminosity function in these panels is shown as the dotted curve, and you can see how things are changing relative to redshift 0 as you go up and up and up in redshift. And the evolution turns out to be complex. This plot here kind of shows a comparison of the best fit X-ray luminosity function shape between different redshifts. There's some technical complexities you can read about in this paper, but you can see the overall evolution pattern is a complex one. But again, quantifying this is very important because it contains a tremendous amount of information about how black holes assembled themselves over cosmic time. Okay, now, in addition to measuring things like X-ray luminosity functions, well, you also want to understand things like, well, how does the supermassive black hole growth proceed as, for example, a function of galaxy stellar mass, m star, and say redshift? Well, detailed measurements have been made of that as well. Here's a recent example showing the long-term average black hole accretion rate in galaxies of a given stellar mass and a given redshift, as shown by these color-coded curves, with the uncertainties shown as the shaded regions. And you can see that supermassive black hole growth averaged over long time scales, measured as I described in more detail in the previous lecture, is a strong function of stellar mass. It rises by orders of magnitude from low stellar masses to high stellar masses. Some of that, of course, is expected because these systems host more massive black holes, so obviously they could have higher black hole accretion rates. But the dependence is very strong indeed, as you can see. And it consistently rises from redshift 0.1 to 0.5 to 0.8, all the way up to a redshift of 4. As redshift goes up and up and up and up, the black hole accretion rate, our measurement of it, long-term time average, rises and rises and rises all the way to a redshift of 4. These measurements have been made specifically from 8,000 AGNs living within 1.3 million galaxies, as measured in a variety of very high-quality surveys that compose one of these wedding cake survey designs, as I talked about in a lecture on surveys. And then this plot here shows kind of the analog of the X-ray luminosity function. This shows the probability of a supermassive black hole having a given sort of Eddington ratio, where that quantity is defined as the X-ray luminosity divided by the stellar mass of the galaxy, given a galaxy's stellar mass and redshift. And you can see here basically this probability function as a function of redshift and as a function of galaxy stellar mass. And this is additional information encoding a tremendous amount of information about how supermassive black holes are manufacturing themselves. And indeed, with these types of measurements, you can connect the X-ray luminosity function with the galaxy stellar mass function, which is very well measured for the general non-AGN galaxy population. And you can, in fact, take the galaxy stellar mass function and combine it with this probability function of black hole Eddington ratio as a function of, again, stellar mass and redshift, and essentially compute what the AGN X-ray luminosity function should be, and you get measurements that agree very well, predictions that agree very well with these measurements. So we now, in fact, can go back and forth between a galaxy's stellar mass function and a galaxy's AGN X-ray luminosity, and the overall AGN X-ray luminosity function for galaxies, with this thing being the kind of interchange that lets you go between those things. So galaxy evolution and AGN evolution has been now connected to quite good levels of quantitative accuracy. Okay, so I have a few more topics to cover. I would now like to tell you a little bit about AGN evolution at high redshift. As you've already seen, we have good constraints now upon AGN evolution reaching up to high redshifts. This is a nice plot from a recent review article. And you can see the overall evolution of the quasar population that I've already talked about. But this plot focuses on the measurements that are being made at high redshifts, starting at redshifts of perhaps around 3 and going all the way up to redshifts of 4, 5, 6, even pushing out to redshifts about 7. And you can see that there is a very strong decline, okay, as you go toward high redshift. And as we've talked about, the expectation there is that decline is being driven by galaxies still putting themselves together and getting themselves organized enough to be able to feed a supermassive black hole. Okay, so that's what's probably causing the decline, but you can see the decline has now been quite well quantitatively measured, pushing to high redshifts. These are the measurements here from, again, wide field, optical, and infrared surveys. You need to go to infrared to probe these very high redshift quasars. But we have also made similar measurements at somewhat lower redshifts in the X-ray band as well, which is very important because, again, that gives you a control on obscuration effects. Here is a compilation of measurements, in this case, showing the space density and the obscuration fraction over here at redshifts of 3 to 5 for high to moderate X-ray luminosity AGNs. So in this panel, this again shows the space density per cubic megaparsec versus redshifts, going out from redshift 3 to 4 to 5 to even 6. And well, in this work, you can see there are 3 different luminosity classes being shown. High luminosity X-ray AGNs, moderate luminosity X-ray AGNs, and low luminosity X-ray AGNs. And you can see there's a clear decline as you push to high redshift, broadly consistent with what is seen from the wide field optical infrared surveys. And if anything, as you go to lower luminosity AGN systems, the decline, if anything, gets faster than it does at high X-ray luminosities, indicating that indeed the whole population, ranging from very luminous systems to moderate luminosity systems to low luminosity systems, is indeed rapidly declining as you push toward high redshift. Again, and you can see this is an order of magnitude or more type effect we're talking about. Furthermore, if you look at the obscured fraction based upon the X-ray spectral data, you find that it's high. Just analyses of the X-ray data. And in this case, we can only really sensitive to column densities above like 10 to the 23, quite heavy obscuration levels. And once you correct for completeness effects, we actually believe that something like 60 to 70% of the AGNs up at these high redshifts as measured from the X-ray surveys, are obscured by substantial column densities. And so there's a lot of obscuration effects present in the high redshift universe, as would broadly be expected given the known evolution of X-ray absorption properties at lower redshift. So if you put together the measurements at very high luminosities, and then high X-ray luminosities, and then moderate X-ray luminosities, and low X-ray luminosities, and we can even stack all the galaxies to set a constraint on them as well, you find that the total power being generated by AGNs is insufficient, pretty convincingly, to drive the reionization of hydrogen in the high redshift universe. So we don't think that the AGNs are responsible for driving cosmic hydrogen reionization at high redshift. Instead, we think that galaxies, the stars in galaxies, particularly the stars in low mass galaxies, are probably primarily responsible for driving the cosmic reionization of hydrogen. This, in fact, has been pretty well established, at least in my opinion, for the past couple of decades. The X-ray data gave pretty convincing indications of this early on, but the data have gotten better and better over the years. And it seems pretty clear that the X-ray, that the AGNs in general cannot effectively drive the cosmic hydrogen reionization. Another point, which I will mention, is that you may be wondering, given that I showed you this plot previously, where again, the black hole accretion rate in galaxies of a given mass rises and rises and rises all the way to a redshift of 4, you might say, well, if this is rising all the way to a redshift of 4, then how is it that the number density is going down? Okay, how is the number density going down starting at a redshift of about 3 if indeed the black hole accretion rate rises and rises and rises all the way to the end of the verse? I mean, how does that happen? Well, the decline in the number density at redshifts above 3, as you're seeing there, we think appears to be driven primarily by the number of available growth sites, the number of available galaxies that have assembled themselves and are able to feed a supermassive black hole effectively. Another possibility could be that, well, you could have many sites available at high redshift, but they're not very good at growing their black holes. But these data show that is not the case. Once you put a growth site together, it will, in short order, start to generate a supermassive black hole. There's no problem once you get a site together in generating a supermassive black hole. But rather, this decline at high redshift is purely being driven, as best we can tell, or at least primarily being driven by the number of available sites that are sufficiently well assembled to grow a supermassive black hole. Not by any problem in once you have a site in actually generating the black hole. There's no problem with that end of things. It's just getting the sites pulled together. That's what's driving this. Pretty convincingly, these data show that. These data combined with these data argue for that point pretty convincingly. Okay, so I will then end our discussion of AGN evolution with a few general, interesting, sort of connected results. One thing which I want to talk about a little bit is the so-called Sultan argument. This is a very important argument put forward back in 1982 in this important paper by Andrei Sultan. And the basic argument says that the summed supermassive black hole growth found in surveys of AGN evolution, like I've been talking about for the past hour or so, well, that sum supermassive black hole growth found in your surveys must add together to be the mass density of local supermassive black holes. The basic argument can be summarized very concisely here. You have basically that the energy produced by growing supermassive black holes will be the efficiency of accretion times the total mass in those generated supermassive black holes times c squared. It's basically E equals mc squared with an efficiency factor of accretion being included. You can then divide both sides of this equation by volume, and you then get over here, well, eta times the mass density of supermassive black holes times over here the energy density in the radiation field. And you also have to put in a 1 plus average redshift factor to account for the fact that the photons are cosmologically redshifted over time, whereas the mass is not. And so you have a cosmological redshifting of the photons in the background field. But basically, this relates the energy density in cosmic backgrounds, or alternatively and equivalently, the some supermassive black hole growth found in surveys to the local mass density of supermassive black holes. And there has been much work done to try to measure the quantities over here. Obviously, we know the speed of light, but we think the efficiency of black hole accretion on average is probably like 5 to 10%. There's some uncertainty there, but that's a reasonable range. And the average measurement of black hole mass density in the local universe is about sort of 6 times 10 to the 5 solar masses per cubic megaparsec. It's a little bit of debate on that number, exactly what it is, but it's around there. And so this is basically a number that serves as a kind of integral constraint on the energy density of accretion. And this lets you set interesting constraints about how, for example, supermassive black holes were generated. In fact, if you take the measurements from the surveys that I've been describing and you work out how much accretion has occurred in those surveys by directly making estimates of how much black hole growth you're seeing, well, you find that you get decent agreement with the expectation from the local mass density of supermassive black holes. This side of the equation and this side of the equation seem to balance pretty well. This is useful because it indicates that, the standard accretion-driven growth of black holes likely is capable of driving most cosmic black hole growth. You don't need some exotic way of making supermassive black holes that doesn't produce radiation over here. You don't, for example, have some need for an exotic accretion mode that doesn't produce much radiation, and that makes a lot of black hole growth. You don't have a need for strong accretion of dark matter that doesn't produce radiation. That's not required to generate the supermassive black holes. You don't need to have massive primordial black holes, primordial supermassive black holes, that is, to explain the black hole mass density. In other words, you just take all the growth that we see, and it adds up pretty well to the mass density of black holes we find in the local universe around us today. The fact that these two terms balance serves as a pretty good constraint on how the black holes were manufactured. And as best we can tell, they were manufactured by standard accretion. You don't need any exotic stuff going on to make these black holes generate. Okay. In fact, people have generalize this even further. You can work this now not just as an integral constraint, but you can work this out differentially, do a kind of differential version of the Sultan argument, and make predictions of the local supermassive black hole mass function. Here is one attempt to do that. Here what you are seeing are observational constraints, I believe is the blue points and the red points and the green shaded region. Those give you reasonable constraints on the local mass density of supermassive black holes as a function of black hole mass. And in this case, these authors have tried to model the black hole growth over cosmic time, and they get a prediction that agrees pretty well with the overall observations, indicating again that you don't need some exotic form of black hole growth in the universe. Standard accretion does a pretty good job, as far as we can tell, of explaining what's out there. Okay, referring back to the previous lecture then, lecture 9, the main growth mode for supermassive black holes, we believe, is accretion of cold gas from the host galaxy. As we talked about in the previous lecture, stellar tidal disruptions only make a minor contribution overall to black hole growth in the universe. They may be important for sort of 10 to the 5 to 10 to the 6 solar mass black holes, but we believe that is in general a relatively small effect, and that most of the black hole growth is accreting cold gas from the host galaxy. That's what does it, not the stars. Furthermore, modeling efforts also indicate that supermassive black hole mergers, which of course are very interesting from a physical perspective, very interesting from the perspective of the generation of gravitational waves, those also seem to be generally of secondary importance compared to the accretion for black hole growth, at least at redshifts of 0 to 4. Although in that redshift range, they may be important at redshifts of less than 1 for very massive black holes. They may be important there, but in general, supermassive black holes are secondary compared to the cold gas accretion. At higher redshifts, redshifts of 5 and above, they may also have an important role. But in this general redshift range, where most of the black hole mass was generated, we don't see that supermassive black hole mergers are somehow having a dominant role in distributing the mass among black holes. They are important and interesting, but they're secondary. Okay, I will then end by addressing one other topic, and this is the topic that I alluded to earlier of the cosmic balance of power. That is, since galaxies formed, you can ask the question, well, what has dominated cosmic radiated power since the formation of the galaxies? Is it supermassive black hole accretion, or is it stellar fusion? Which of those produces most of the power since the galaxies put themselves together? And there's been a lot of uncertainty on this point over the years. Here is, in fact, a press release from 1999 by a distinguished astronomer down here, proposing that black holes may supply up to half of the universe's energy output. So people quite legitimately thought that you could argue that half of all cosmic power, the cosmic balance of power, could be at least half from supermassive black holes. Well, with all the survey measurements, we have now constrained this much better than we could back in 1999. And this goes to this issue of the contribution of active galactic nuclei to the cosmic background. So this is a nice plot showing the energy density in various observed cosmic backgrounds as a function of wavelength and as a function of photon energy up along the top here. Up here in the X-ray band, we now know quite convincingly that the cosmic X-ray background is primarily produced by active galactic nuclei. So this is probing growing supermassive black holes in the distant universe. We then have a cosmic optical background. We now know that is from stars. And then we have a cosmic infrared background. We believe that's from dust. I'll say more about the cosmic infrared background momentarily. That's important. And then, of course, the dominant background of all of the cosmic is the microwave component, which is from the primordial plasma associated with the Big Bang. Leaving aside the microwave background, so focusing on emissions since the formation of galaxies. So that's this infrared component, this optical component, and this X-ray component. Well, you can ask the question, what makes most of the power? Well, just looking at this straightforwardly, it looks like, well, the optical component is bigger than the X-ray component, so that seems to be dominant in terms of the stars. But a big question, which was around for many years and which led to studies like the one described here, is this infrared component. How much of this infrared component, which is from dust, re-radiating waste heat, how much of that is from stars versus AGNs? Well, this was uncertain because it was uncertain exactly how the AGNs evolved over cosmic time. It was uncertain how much obscuration was present. And if you had a lot of very powerful, highly obscured AGNs in the distant universe, in fact, much of this infrared background could plausibly have been from obscured active galactic nuclei. However, now that we have very high quality X-ray surveys, very high quality infrared surveys, we can look at the growing supermassive black holes, which we think we have a quite complete census of. We can measure their infrared powers, and we find that the infrared component is sort of 5 to 10% from the AGNs, but is primarily from the stars. And so thus, when you work out your sums overall, it appears that supermassive black holes have made sort of ballpark numbers like 5 to 10% of cosmic power overall since the formation of the galaxies, and that stars made 90 to 95% of cosmic power. That is, in this cosmic balance of power, the stars win. They make 90 to 95% of cosmic power, with supermassive black hole accretion making sort of 5 to 10% of cosmic power. That's how this cosmic balance of power comes out. If you want to see more details of that, you can see section 5 of this review. And that's where I will end today in our discussions of AGN evolution. Thank you.